everyone, welcome back to Intermediate Algebra one more time. Today we're in section 10.2 where we're going to be talking about rational exponents. So there is a way that we can change out of radical notation and into rational exponent notation. You remember that the word rational always means we're dealing with fractions, so these are exponents that are in a fraction form. In today's video, I'm going to show you how to use exponential notation for all nth roots. That will replace radical notation whenever we want it to. And I'm going to show you how to use expressions that are in the form a to the m over n power. We're going to talk about converting between radicals and rational exponents. And we're going to talk about using the exponent rules with rational exponents. So here we go. So as I kind of mentioned before, instead of representing roots with radical symbols, we can represent them in exponent form using rational exponents. So we know that the square root of 3 squared would be 3. And we also know from our exponent rules that when you have an exponent raised to a power, you multiply the exponents. So here, for example, 3 to the 1/2 raised to the second power means we would multiply 1/2 times 2, which is 1. So that would make 3 to the first power, which is also 3. So look, if we square the square root of 3, we get 3. And if we square 3 to the 1/2, we also get 3. And so it seems like the square root of 3 is the same thing as 3 to the 1/2. And that's exactly how it works. So here is a definition for us. If the nth root of a is a real number, then a to the 1 over n power means the same thing as nth root of a. For example, the third root of 2 is the same as 2 to the 1/3 power. The fifth root of 18 is the same thing as 18 to the 1/5 power. And the square root of 20 is the same thing as 20 to the 1/2 power, because even though we don't have an index here, we know that this is the square root, and therefore the denominator on our exponent is going to be 2. So the bottom line is the denominator of the rational exponent is the same as the index of the radical. Now let's look at example 1 together. So this says evaluate each exponential. And I'm going to do that by switching into radical form just to help you think about what's going on. It's not really necessary to switch into radical form in order to do the evaluation, but I'm just trying to help you get your thoughts in order. So just keep that in mind as you're doing your homework. So here we have 64 to the 1/3 power. And the first thing we want to do is convert this to radical notation. So we remember that the denominator of the exponent is the index of our radical. And we're going to write third root of 64. So now we're asking ourselves, what is a number that I could raise to the third power and get 64? And that number is 4. 4 to the third power is 64. Okay, here in part B, we have 100 to the 1/2 power. So we know the 1/2 power indicates the square root, and the square root of 100 is 10. And remember, when we're talking about an even root, the radical always has to give you a positive value. In part C, we have negative 256 to the 1/4 power. So remember that because this base is not in parentheses, the 1/4 power only applies to the 256. The negative is out front. You can kind of think of it as a multiplier or a coefficient. So we're going to have negative fourth root of 256. Now what is a number that I could multiply times itself 4 times and get 256? Well, we know the square root of 256 is 16. 16 times 16 is 256. And the square root of 16 is 4. So that means the fourth root of 256 is 4. And because of this negative, we're going to have negative 4 as our final answer. Here in part D, we do have the base in parentheses. So the negative is included in what this exponent is affecting. So we're going to have to write fourth root of negative 256. Now we know that any number raised to the fourth power will give a positive result. So it's not possible to find a real number whose fourth root is negative 256. So we're going to say that the fourth root of negative 256 is not real. In part E, we're looking at negative 32 in parentheses to the 1/5 power. So we're going to write fifth root of negative 32. Now remember, when it's an odd root, we can take the odd root of a negative number and we'll get a negative answer, because a negative raised to an odd power will still give a negative result. Okay, now we need to think of a number that we could raise to the fifth power and get 32. And of course that number is 2. 2 times 2 is 4, times another 2 is 8, times another 2 is 16, times a fifth 2 is 32. So the fifth root of 32 is 2, but the fifth root of negative 32 is negative 2. And again, it was only possible to get this negative answer because we're doing an odd root. Okay, finally here in part F, we have 1/8 raised to the 1/3 power, or we could write it as the third root of 1/8. Now it just so happens that both 1 and 8 are perfect cubes. So the cube root of 1 is 1 and the cube root of 8 is 2. And so the cube root of 1/8 is 1/2. Now let's go back and look again at the difference between part C and part D, because we touched on it, but we need to really make sure we understand this. So I'm going to hit this one more time. Notice that the only difference between these two is that in part C we do not have parentheses and in part D we do. So in part C, the exponent is affecting the 256, but the negative is not affected by the exponent. So when we write this in radical form, the negative stays out front, and the 256 is what goes under the radical. And so what's happening here is that we're taking the negative fourth root of 256. Over here in part D, we do have parentheses. So when we write this in radical form, all of this goes under the radical. And so what's happening here is that we're taking the fourth root of negative 256. I want you to see the difference. When there are no parentheses, the negative is outside the radical, and we're taking the negative fourth root of that number. But when there are parentheses, the negative goes inside the radical, and we're trying to take the fourth root of a negative number. And as we saw in the last slide, the fourth root of a negative number is not a real number, but the fourth root of this positive number is 4, and when there's a negative in front, we get negative 4 as our final result. Okay, now we're going to move on and talk about a to the m over n. Previously, the top number of our exponent has always been 1, but now we're going to look at what happens when the top number of the exponent is a different number besides 1. So first of all, we want to remember, and you should already know, that the index of the radical is the denominator of the exponent. Now, if the number under the radical is being raised to some power, that power is going to be the top number of your exponent. So that number is going to be the numerator of your exponent. So here it is in math notation. A to the m over n power just means a to the 1 over n, that's the nth root of a, raised to the m power. Now, be careful and pay attention, because if a to the 1 over n power is not a real number, then a to the m over n power is also not a real number. In other words, we can't get a final answer if the root part doesn't give us a real number. Now, you can use your calculator to evaluate a number raised to a fractional exponent as long as the base is positive. But you also need to know how to evaluate mentally without a calculator. And so we're going to practice that. To evaluate an expression with a rational exponent, first you're going to use the denominator of the exponent to get the required root, and then use the numerator of the exponent to get the required power. So think about it this way. As long as you're talking about a base that's more than 1, if you raise that base to a power, you're going to get a number that is bigger than what you started with. if you take a root of that number, you're going to get a number that's smaller than what you started with. So to keep the arithmetic easy in our heads, we do the root first. That gives us a smaller number instead of a bigger one, and then it's easy to get the power. If you try to do the power first, you're going to find that you're going to have to work with very large numbers, and that makes it harder to do in your head. So let's practice here in example 2. It says evaluate each exponential, and we're going to try to do this without using our calculators. So first we're going to practice writing this in a form that makes it easy for us to evaluate, and I'm hoping that writing it in this different form will help you get your thoughts in order. And then when you get strong at this, then you can leave off writing the separate steps and you can just do the whole thing in your head. So first of all, part A says 36 to the 3/2 power. So remember, we said we do the root first. So we're going to write this as 36 to the 1/2 power raised to the 3rd power. Now 1/2 times 3 is 3/2. So I have not changed the value of our expression. I've just written it in a way that shows me which step to do first. So we remember that the denominator of the exponent tells us which root to take. So if we write this in radical form, we'll have square root of 36 raised to the 3rd power. And we know that the square root of 36 is 6, and then 6 to the 3rd power is 216. If you didn't know that by heart, you might have to jot that down and work it out, but you still would not need a calculator for that. Okay, here in part B, we have 125 to the 2/3 power. So first let's write it in an exponential form that shows the root first and then the power. So the denominator is 3. So we're going to have 125 to the 1/3 power, and then we're going to raise that to the 2nd power. Now, if we write this in radical form, the 3rd root of 125 looks like that, and then we need to square that. So we know that the 3rd root of 125 is 5, and so 5 squared is 25. So 125 to the 2/3 power is 25. You see how if you do the root first, you don't really need a calculator? The 3rd root of 125 is 5, and 5 to the 2nd power is 25. Here in part C, notice that this base is not in parentheses, so that means the negative is not part of the base, and therefore the negative will go outside the parentheses when we split this exponent up. So we'll have negative 4 to the 1/2 power raised to the 5th power. Now we know that this 1/2 power represents the square root, so let's just write square root of 4 is 2. So we'll have negative 2 to the 5th power, and the 5th power of 2 is 32. But notice I'm not including the negative in what's being raised to the 5th power, so the negative is just going to sit there, and 2 to the 5th is 32. So we end up with negative 32. Here in part D, we do have parentheses, so the negative is included in what the exponent is acting on. So we're going to have negative 27 all to the 1/3 power, and then we're going to raise all of that to the 2nd power. Okay, the 3rd root of negative 27 is the number that we could multiply times itself 3 times and end up with negative 27. So the 3rd root of negative 27 would be negative 3, and then negative 3 squared would be positive 9. And finally, here in part E, we have negative 100 in parentheses raised to the 3/2 power. So the parentheses mean that the negative is included in what the exponents are acting on. So we're going to have negative 100 to the 1/2 power, and then all of that raised to the 3rd power. Let's look at that in radical form. So because this is in parentheses, the negative is going to belong under the radical, and then all of that would get cubed. But the problem is that we can't find the square root of negative 100. We can only find the square root of positive numbers. Negative numbers do not have a real number square root. So it doesn't matter what would happen with the 3rd power. This number inside the parentheses is not real, and therefore we cannot get a real answer. Okay, now we're going to move on and talk about the negative exponent rule with rational exponents. It works exactly the same for rational exponents as it does for integer exponents. So if you have a to the negative m over n, you can make that exponent positive by moving that expression to the denominator, as long as your base is not 0, of course, because then you would have an undefined expression. So in example 3, let's practice writing each of these with a positive exponent, and then we can evaluate. So here we have 16 to the negative 3/4. So remember that to eliminate the negative exponent, we will move that expression to the denominator. So now I have 1 over 16 to the 3/4. And now we will write this in radical form just for the practice of it. So remember, we're doing the 4th root because 4 is the denominator of our exponent. So we're going to have 1 over the 4th root of 16, and then this whole denominator is going to be raised to the 3rd power. Now the 4th root of 16 is 2, so now we have 1 over 2 to the 3rd power, and 2 to the 3rd is 8, so now we have 1 over 8 as our final result. In part B, we have 25 to the negative 3/2 power. So again, to get rid of the negative, we move all of this to the denominator. So we'll have 1 over 25 to the 3/2 power. And again, the 2 in the denominator means that we're finding the square root of this base. So I'm just going to separate it out in exponential form. I didn't even go to radical form this time. I did over here, I didn't here. As long as you know what root you're getting, it doesn't matter for your own scratch work which way you write it. So here I have 1 over 25 to the 1/2 raised to the 3rd. So you see that the denominator of our exponent tells us which root to take, and the numerator of our exponent tells us which power. So I have here the 1/2 power of 25, so that's the square root of 25. So now I have 1 over 5 to the 3rd, and 5 to the 3rd is 125. So I end up with 1 over 125. Now here in part C, we have 8 over 27 raised to the negative 2/3. And we remember that a negative exponent applied to a fraction just creates a reciprocal for that fraction. We didn't really think of it that way here because these bases were whole numbers. But here in part C, if I write this as 1 over 8 over 27, I'm going to have a fraction within a fraction, which can be confusing to look at. So here, let's remember that the negative exponent causes the base to do a reciprocal. So instead of having 8 over 27 to the negative 2/3, we can have 27 over 8 to the positive 2/3. These two expressions are equivalent. And now we can write this as the 3rd root of this fraction, all squared. So I'm going to write the 3rd root of 27 over 8, all raised to the 2nd power. Now both of these numbers under the radical are 3rd powers. 27 is the 3rd power of 3, and 8 is the 3rd power of 2. So the 3rd root of 27 over 8 becomes 3 over 2. And of course I've got to square it because of this outside exponent. And so now I can do 3/2 to the 2nd power, and that's just 9 over 4. Now, we've pretty much already touched on the topic of this slide, but I do want to just point out that when you're converting an expression with a rational exponent to a different form, there are 2 ways to do it. One way is to have that top number of your exponent go under the radical. You can do that, or you can do what we've been doing, which is to have the top number as a power outside. I really like this way because it says do the root first, then do the power. This way actually says do the power first and then the root. It's not wrong, but it's harder to work with if you're going to try to do this in your head. So the nth root of a to the m means to first raise the base to the m power and then take the nth root. On the other hand, the nth root of a raised to the m power means to take the nth root first and then raise that answer to the m power. Technically, a to the m over n can be written either way, but when you're in MyLabs Plus working on homework, they will give you instructions that tell you which way to express the answer. So you'll want to be sure and not use this middle way if they're looking for the last way, which is usually the case. They usually want you to do the root first and then the power. Okay, here in example 4, we're again practicing converting these to radical form. So it says write each exponential as a radical, assume that all variables represent positive real numbers, and use the definition that takes the root first. So we'll have the radical inside the parentheses and the top number of our exponent applying as a power afterward. Okay, here we have 13 to the 1/2 power. So the 1/2 tells us that we want the square root. So we'll have the square root of 13, and technically this is raised to the first power, but there's no need in writing that first power out there because anything to the first power is itself. Okay, moving on to part B. We have 6 to the 3/4 power. So first we want to write the fourth root of 6, and then we want the power 3 outside of that. Now we're not asked to evaluate this, we're just asked to write it as a radical. So here it is as a radical with the root coming first and then the power. Here in part C we have 9 times m to the 5/8. Now I want you to ask yourself, what is the 5/8 applying to? Well, because of order of operations, the 5/8 only applies to the m. The 5/8 is not affecting the 9. If you needed the 5/8 to apply to the 9, this whole thing would have to be in parentheses. Because it's not, the power on the 9 is a 1, and we don't have to write it. So when we write this in radical form, we're going to have the 9 outside, and then we're going to have an 8th root of m, and then this whole radical is being raised to the 5th power. See how the 9 sits outside of that, and it's very important. Same thing on part D. So we have 6x to the 2/3. So the 2/3 exponent is only applying to the x. So the 6 will stay outside. We'll do the third root of x, and then we will square that whole thing. On part E, we have r to the negative 2/3 power. So first we want to eliminate this negative exponent, so we will write 1 over r to the 2/3 power, and then we will put the third root of r, and we'll square that whole denominator. For part F, they're asking for the 1/2 power of this expression in parentheses. So the 1/2 power is the square root, so we'll just put all of this under a radical. And of course, if we needed parentheses out here, it would be to the first power, but because the first power doesn't change anything, we don't have to write that, just like we did not write it in part A. Now, sometimes when you have a radical expression, writing that radical expression with rational exponents will help you simplify the radical a little bit. So that's what we're going to try here. In example 5, notice it says write each radical as an exponential and simplify if possible. Assume that all variables represent positive numbers. So that's just code for don't worry about using absolute value bars. Okay, in part A, we have square root of 10. So we know that the square root is the 1/2 power. Remember that the index of the radical tells us the denominator of our exponent. So this is going to be 10 to the 1/2 power. Now that cannot be simplified. So we're just going to leave this in this form. Now in part B, we have the square root of 5 to the 4th. If we write this in an exponent form, we know that this means 5 to the 4th is being raised to the 1/2 power, and we know that 4 times 1/2 is 2. So 4 times 1/2 is 4 over 2, which reduces to 2. So this is 5 to the 2nd power, which is 25. A similar thing happens in part C. We're asked to evaluate the 4th root of 3 to the 8th. Now think about it. If you had to work out 3 to the 8th first, you would get some giant number, because 3 to the 4th is 81, and then you'd have to multiply by 3 4 more times. So that number is going to get really big. And then you've got to do the 4th root of that giant number. That's what we're trying to avoid. So here, all we have to do is switch into exponent form. So we'll have 3 to the 8th raised to the 1/4. Now we multiply these exponents. 8 times 1/4 is 8/4, which is 2. So 3 to the second power is just 9. See how going through the exponents helped us get to the final result much easier than if we tried to just do it the way it's written. And here in part D we have the 6th root of z to the 6th power. So they told us not to worry about what would happen if z was negative. They said assume that all variables represent positive numbers, so we don't have to think about absolute value bars or anything. But if we write this in exponent form, we'll have z to the 6th raised to the 1/6, because this index tells us what should be the denominator here. And 6 times 1/6 is 1. And of course z to the first is just z. So this all simplifies to just z. And finally, I want us to get just a little bit of practice with the product rule, power rule, and quotient rule. They will all work the same way as they did when we had integer exponents. So here in example 6, it says simplify each expression and assume all variables represent positive real numbers. So again, they're telling us that when we encounter variables, we don't have to worry about absolute value bars. All right, here in part A, we have 2 to the 1/2 times 2 to the 1/4. Now we know that when the bases are the same, we can add the exponents. Now I want to make sure you understand, I'm not saying that this looks like multiplication, but it's really an addition problem. It is a multiplication problem. But when the bases are alike, multiplication means adding the exponents. So we'll have to figure out what is 1/2 plus 1/4. And we'll just do that down here as scratch work in blue. So when we add fractions, we need common denominators. I'll have to change this 2 to a 4. So I'll need to multiply that by 2 over 2. And we see that 1/2 plus 1/4 is really 2/4 plus 1/4, so that's 3/4. So the answer to 2 to the 1/2 times 2 to the 1/4 is 2 to the 3/4. On part B, we have 5 to the 2/3 divided by 5 to the 7/3. So this is division. That means we will be subtracting the exponents. Now, when I subtract, I like to do the larger exponent minus the smaller exponent. That way I end up with a positive number. And I know that the leftover power is going to go where the larger exponent was. In this case, the bigger power is in the denominator. So I'm going to do 7/3 minus 2/3, which of course is 5/3. Because the denominator had the larger power, I know that the 5 power from the top is now canceled out, and that's going to leave a 1 in the top, and my 5 to the 5/3 is going to go in the denominator. Now in part C, we have x to the 1/2 times y to the 2/3, all raised to the 4th power, and that's all over y. So now what does this 4 mean? This means that we will apply the power rule. We will raise every factor in this product to the 4th power. And so we'll have x to the 1/2 raised to the 4th times y to the 2/3 raised to the 4th. And notice that that does not apply to the denominator, so the denominator is still just y. All right, now the power rule tells us to multiply these exponents together. So we'll have 1/2 times 4, which is 4 over 2. And then we'll have 2/3 times 4, which is 8 over 3. And then we'll have still y in the denominator. And now, I need to subtract 8/3 minus 1 to get these y factors combined. So I'll have to say 8/3 minus 1, I'll need a common denominator. So multiplying this 1 by 3 over 3, I see that that is 8/3 minus 3/3, which is 5/3. Now again, the larger power was in the top, so this y in the bottom has been wiped out, and we're going to get x to the 4 over 2, which is x squared, times y to the 5/3, because 8/3 minus 1 is 5/3, and that's it. Now you're going to see rational exponents throughout college algebra and beyond, if you have to go beyond into business calculus or anything like that. So don't gloss over this, but make sure you understand it and think about it. And if you'll take your time and think about it, it will start to make sense to you. And if you'll practice with it, all of these right here seem really difficult right now, and your head may be spinning a little bit. But if you'll practice them in the homework and then come back and look again and just think about it over and over, things begin to get easier. Everything that's new makes your head spin a little bit, but that's okay. When you review, and you review and you review, things begin to clarify and come into focus for you. So don't underestimate the power of reviewing that, and I'll see you in the next video.